Thank you everyone for coming to this talk, and welcome from my side as well. So today I'm going to present you the work that was published last year in the journal Knowledge-Based Systems, which is Elsevier's journal. And the paper is titled FairBoost, Boosting Supervised Learning for Learning on Multiple Sensitive Features. I chose this work because it's mature enough, but although it's not computer vision and maybe not as close to you, but it would be a good introduction into fairness in machine learning. So we all know about machine learning, and currently we use it to automatize some human tasks such as decision making. And we sometimes use it without thinking twice about it. They have capability of extracting patterns that are hidden in data and can often be visible to the human eyes. So they extract them and learn from them. And that is their strength, that is why we use them. And that's why we don't think much about them, because we are used to them. But how do we get to that point that we use them in real-world applications? So we developed some machine learning model, we give them some data sets, they find the patterns, they learn from that patterns, and we have a trained machine learning model, then we evaluate that model. And how do we do that? We measure some metrics and we say that the model is good, right? But how do we know that the model is actually good? We usually use some of the common metrics, for example, accuracy, and we say model is good if it has high accuracy, right? But can that model fail us even though they have good performance, even though they have high accuracy? These are just a few examples from the machine learning models failing us in real-world applications, and these are the examples from big tech companies. So in this example on the right, we can see Google tagging black people as gorillas. We can see Nikon cameras that had real-time detection of people blinking, mistakenly showing Asian people as if they were blinking, although they were not. This on the left side is actually a case that is covered by Netflix documentary called Bias, and is an MIT researcher which face couldn't be recognized by a robot until she put a white mask on it. And behind that is also Amazon's algorithm. And here as well in the middle we have Amazon case of deciding which customers are eligible for same-day delivery, and although they do not consider race, they turn out to be racially biased because the race was leaking throughout other features that they were using to train their models. So we can see that models that are thought to be good had some flaws in real life. And what are those flaws? We call it unfairness. But while we wait to see a bit how we can mitigate that unfairness in machine learning models, there is a question of what is actually fairness. So when I first came into this field, I try to find and define what fairness is, because in order to measure something, we need to be able to define it in words and then mathematically. But actually, even though it somehow we understand by default what fairness actually is, and if we will be given some example, all of us would know to answer if something is fair or not, but there is a possibility that not all of us would agree on that. So that comes from the lack of the standard definition of fairness which are not agreed upon nor by psychologists nor social scientists, and that leads to the lack of standard mathematical definitions, leaving the fairness for free interpretation to us as machine learning engineers. So currently we have more than 20 metrics of fairness which can be contradictory to each other and cannot be all achieved at the same time. And that is one of the big challenges of this field. We can have also individual and group fairness. Individual fairness is based on similarity between individuals and machine learning models treating fair every individual. So we decide some similarity between samples based on some of the features that are correlated to the target feature. But as we can see here, those individuals can be separated in groups, but we wouldn't compare that groups between each other. On the other hand, we can have group fairness, where the samples would be separated in groups based on some common feature. For example, here we would have shape as a common feature, and then we would try to have to treat fair every group that we have here. So when humans are making decisions, they are prohibited to use certain human traits in that decision making, or at least it's prohibited for that trait to be deal breakers, and that is prohibited by law, and those are discrimination laws. Until now, only recently, at least in Europe, we saw some kind of regulations that could regulate the use of human traits for training machine learning models and decisions made by machine learning models, such as AI Act, but still a lot until now was not regulated, and that each human trait could be used for decision making or even as a deal breaker for some decisions. So those human traits are called sensitive features, and as I said, should not be deal breakers. Most commonly, we can see gender, age, race, marital status, religion, and so on. We can also have in datasets, of course, if datasets are describing some people, we can have more sensitive features. And we can have also proxy sensitive features, which are features that we might not know that are correlated to sensitive feature, but actually are and are leaking the fairness. So we can then separate these samples into groups based on the values of that sensitive features, and we call the values of sensitive feature categories, sensitive feature groups, which are basically categories of those sensitive features. So if we would have gender, then the sensitive feature groups would be male, female, and other. If we would have, I don't know, race, then the groups would be Asian, white, black, and so on. In this work, we focus on group fairness, and we strive for equal quality of service, which basically means that we want machine learning model to offer equal quality for all sensitive feature groups. And to understand better what does that mean, so currently we have something that would look like this. So our model that performs relatively good in terms of accuracy, but really different for each sensitive feature groups. So here we would have a good quality, but for fairness. And what do we want? We want a model that would perform the same for each sensitive feature group, but what can happen? We can have a fair model which then fail to provide us with a good classification, overall classification quality. So we have good fairness, but poor quality. So what do we actually want? We want something that looks like this. So we can have slightly worse model in terms of overall classification quality, but achieving the fairness by treating every sensitive feature group the same. So the objectives of the fair machine learning field would be to improve fairness and achieve good quality of machine learning models. And where can we address that fairness? We can do it in pre-processing by manipulating the data set we have in order to eliminate the discrimination that can be found in data. We can do it in processing, that is, of course, if the model is available to us and if we are able to change, then we can prevent the learning of the unfair patterns, and we can then lastly do it in pre-processing, which is usually done when the model is not available to us. So we see machine learning model as some black box. We get it as it is, and then we can only do something with outcomes, which is basically reassigning the labels usually. And what causes this unfairness? The unfairness usually comes from the data itself, but due to the lack of the other data sets, we are forced to use the ones we have. And those data sets can have imbalanced data and low quality data, which can be specific for one sensitive feature groups, which would then mean that machine learning model would then be less favorable to those models in terms of imbalanced data. If we have, for example, some sensitive feature group being underrepresented, then that would mean that the model would most probably be biased against them. Same goes for low quality data. For example, if we use the different measurement tools, if we have incorrect data, if we have some missing data, which can, once again, if it is correlated to one sensitive feature group, can lead to model being biased against them. And in the end, we can have complex patterns, which if they are characteristic of one sensitive feature group, can lead for those samples being more challenging to the model, and model not learning them as easily as they learn others, once again leading the model to be unfair toward them. And those are the causes that we've seen, but as I said, we are forced to use the data as we have it. So those are actually the consequences of the bias in data. So as I described, this unbalanced low quality data can be representation bias or the measurement bias, which we all know what they are, but they can also be caused by historical bias and social bias. Historical bias is when data is reported, when data is reported, it keeps the context of the time in which it was reported. So it is influenced by the time in the context and decisions in which people lived in back then. And social bias in when in data it is captured prejudice, discrimination, and similar. So as I said, we want to improve fairness and maintain good quality. We want to do it in new processing because we are able to interfere with the machine learning or the learning of the model. And how do we want to do that? Well, why would we want to reinvent the wheel when we already have good existing models? So we only want to try to include fairness in them to such extent to improve fairness without significantly losing the good quality of the models we already have. So as you can see, objectives change a bit from improving fairness stays the same, but from achieving good quality, we only want to maintain the quality we have. So using standard machine learning models would be the first logical step here. And why use only one model when there are techniques to merge more of those models to achieve better performance? And those would be ensemble models, which would then have base estimators or weak learners, as we call them. And it is a mostly iterative approach, where we teach some model and then merge the outcomes of all of those weak learners. There are different techniques then for merging those outcomes, and one of them is a boosting technique, which is the base of this AdaBoost algorithm, which is widely known in classification tasks. So the point of the boosting technique is actually iteratively improving incorrectly classified samples by reweighting them. So at the beginning, we initialize weights for each sample in a training set to the same value. Then we train the model, make a prediction, evaluate the model based on the classification quality, and calculate here also estimation error. And based on the estimation error, we would reweight the training set in such a way that we would increase the weight of the incorrectly classified samples, which would be the more challenging ones and the ones that model should pay attention more when learning. Then, if the NDF criteria is reached, we would just return the ensemble and have our machine learning model. What is ending criteria? It is classification which can be perfect or achieving a certain number of iterations that were given in the beginning. If the criteria is not reached, then we will go back to training next model with the new weights we have here. So with this model that is performing good, we wanted to introduce fairness into it. So we added a few steps that are here marked with red. So these two steps. So besides evaluating each base estimator with only classification metrics, we also use fairness metrics. For fairness, we use fairness of each sample I as the biggest difference between the sensitive feature groups which achieve maximum accuracy and the sensitive feature group to which sample belongs to, and then use that for calculating the new weight of that sample, where we would, in the existing AdaBoost equation, add that fairness of that sample with the fairness weight factor, which is a factor in which we want to say how much fair we want our model to be. So that can be a value between 0 and 1, and if it is 0, then we would have original AdaBoost. If it is 1, then we would only strive for perfect fairness. In order to evaluate this approach, we performed the experiment. We used single and multiple sensitive features because recent work is mostly using only single sensitive features and only binary sensitive features, whereas we use also like categorical ones that have more than 2 categories, and the multiple sensitive features we use stratified file for cross-validation, and for the algorithm we use mostly default values of scikit-learn library. We compare the FairBoost algorithm to the decision tree. So decision tree is a base estimator of all of these ensembles. We use original AdaBoost and the Fair AdaBoost, which is another version of this algorithm presented at the data conference. We measure accuracy and F-score as a classification metrics, which are better when the values are higher, and the equal results difference and demographic parity difference, which are fairness metrics, and better when the values are lower. We use 4 data sets which are notorious for their unfairness. These are publicly available data sets. The first one, called the adult data set, is all of these are used for binary classification tasks. So in adult data set, we decide if person is will earn more than 50K per year or not. In arrhythmia, self-explanatory if someone has arrhythmia or not. In drugs data set, we classify someone as heroin user or not. And in German credit data set, we classify someone as eligible for credit or not. Here you can see the number of instances, which are pretty different, number of features, with medical one having the most. Here you can see the sensitive feature. For example, here in adult we use age as single sensitive feature and gender plus age, meaning that we use multiple sensitive features. And then regarding that, how many sensitive feature categories we have and observe at the end. So now that we know the data, let's go to the results. So these are the results of single sensitive feature for each data set and sensitive feature. This is the accuracy, and we can see the first column is original AdaBoost, and the fourth one is our proposed FairBoost. We can see that usually, except in arrhythmia, they perform similarly, and same goes for F-score. Once again, arrhythmia beats dental, but in other data sets, we can see the first and the fourth column usually achieves the same values. And speaking of fairness, we can once again data set sensitive features and first column AdaBoost, original, and the fourth one FairBoost. We can see that in demographic parity difference, FairBoost achieves lower results than original AdaBoost, meaning that the results are better when FairBoost is used. When it comes to equal results difference, we can see that the difference is not that much as in demographic parity, but once again, these are 2 metrics capturing different aspects of fairness, meaning that we cannot improve both of them, we cannot achieve both of them at the same time. This is just here to show us the different aspects of wider picture of fairness. So let's look at the results of multiple sensitive features. So we use ethnicity and gender, age and foreign worker, gender and foreign worker. Once again, we can see that accuracies are mostly the same in original and proposed approach, as well as for F-score. When we look at the demographic parity difference, we can see the biggest difference in the German credit data set. And yeah, in both of these sensitive feature combinations, whereas in drugs, actually the fair AdaBoost achieves the best results. And for the equal results difference, as they are being, because as they have value of 1, meaning that we do not mitigate unfairness, but still in the German data set we can see that FairBoost is a bit better. So to further analyze our results and to further show our contribution, we do the statistical analysis of these results. We performed Wilcoxon sign rank test with Holmbohm-Ferroni corrections, post-hoc corrections, where row values are transferred into ranks, and here we show mean ranks. So the first picture on the left is for single sensitive feature and multiple sensitive feature. this is a use case for the adult data set with age-sensitive feature. So that's why only one image is for each use case. And we can see that in classification metrics, AdaBoost achieves the highest rank, meaning it is the best, and in fairness, FairBoost achieves the highest rank, meaning it is the best for those metrics. Same goes for the multiple sensitive features. And if you remember from the algorithm I told you, we used fairness weight as a factor to decide how much fair we want our algorithm to be. And here we did analysis on the same setup, meaning a data set with age-sensitive feature, to see how this fairness weight impacts the results. So we measure fairness metrics, demographic parity difference, and equalized odds difference in each iteration, meaning for each base estimator in ensemble, using fairness weight of 0.25, 0.5, and 0.75, because using 0 would mean that we use only original AdaBoost, and using 1 would mean that we strive only for fairness, which didn't show good results. But here, using fairness weight of 0.25 in both cases, we see that already in half of the iterations, performance starts to stagnate a bit. So we may not use all the 50 iterations that we have in order to improve our results. Whereas in fairness weight to 0.75, we have this line going all over the place, meaning that it doesn't really mitigate unfairness. It doesn't really learn us in that direction that we hope to. So using somewhere around 0.5 would be somehow the most perfect, the most optimal one, because we have that kind of a downward trend which uses all the 50 iterations. And actually this fairness weight of 0.75 showing us that striving for perfect fairness actually deepens the unfairness itself, because if you see it ends not on such low values, only confirms our assumptions that even in real life, when we want something to be really, really, really fair, it can actually be really unfair from some different point of view. Additionally, we also used the shop explanation method to show which features impact the original AdaBoost and the FairBoost for all fairness weight values that we saw before. And here we show the difference between the FairBoost and AdaBoost shop values, which means that if the value is positive, these features contributed more to the FairBoost algorithm, whereas if the value is negative, that means that these features contributed more to the original AdaBoost. And we can see here that features such as marital status, like here and here, and the relationship being here, 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 and occupation can heavily affect the unfairness of AdaBoost, because we can see them contributing a lot more to the AdaBoost than FairBoost. And actually what is interesting is that these features are the ones that can be found in the discrimination laws, especially marital status, and that shows that there is historical, there were some opportunities where people use these features for discriminating people, and this also confirms that unfairness comes from the data and that is learned by the model, because it is established in data that younger people are more likely to be lower paid than the older people, even though they have higher education, and that females can have are less likely to be paid more than 50K per year than the males, even though they also can have higher education. So this showed us that fairness can successfully be addressed in processing phase by incorporating it in existing machine learning models without significantly losing in classification quality. We show that this algorithm is pretty flexible. You can include whichever fairness metric or whichever classification metric you want. These iterative approaches that reweight the samples allow clear and interpretable way for including fairness in it and understanding why we did it and how we did it. While further analysis show that aiming at perfect fairness further deepens the unfairness itself, as I said before, and these conclusions about reweighting the samples kind of resembles to neural networks, and that is why this work leads to next steps, including fairness in neural networks themselves. So thank you everyone for being here, and if you have any questions, I am available. And if I can say before questions, I urge all of you in maybe not during the PhD, but sometime if you're doing machine learning for the real world application, think about evaluating your models, not only in terms of performance, not only in terms of what is good for business, but also what is good for the people that would have consequences of this model.